You know, a lot of folks think the Internet of Things is just slapping a microchip on a toaster and suddenly calling it smart, right? But today, in this explainer, we're tackling something way bigger. We are diving into a massive puzzle, exactly how we activate the physical world. The reality isn't some one-size-fits-all tech. It's actually a fascinating, super complex spectrum of architectural choices. So let's just dive right in. So, I want to pose this direct question to you. What does it actually take to activate the physical world? We've really got to stop looking at IoT as just software magic. Fundamentally, it's a massive physical systems engineering challenge. You are taking digital architecture and literally forcing it to obey the laws of physics, geography, and human movement.
Look at the shift we're making. We started with these legacy machine-to-machine or M2M silos. Think of them like isolated little islands of hardware, zero scalability. And now, we're moving toward true modern IoT ecosystems. We're talking internet-integrated layers using scalable, software-defined networking and global device addressing. But here is the absolutely crucial point. That transition, moving from isolated M2M to scalable IoT, introduces incredibly complex constraints. You can't just plug and play. Every single application domain out there has to solve its own unique puzzle.
Now, before we look at specific environments, we need a measuring stick. There are 4 foundational dimensions of IoT architecture that literally every domain has to balance. First up, network protocol and range. Are we covering a few feet with Bluetooth or an entire city with LPWAN? Second, latency tolerance. Can this data afford to be delayed a few seconds, or is it mission critical right this very millisecond? Third, edge versus cloud reliance. Are we constantly pushing data up to centralized cloud servers or processing it locally on the edge to save bandwidth? And finally, security and privacy risk. Balancing those 4 dimensions, that's the secret sauce. That is how we solve the puzzle for any given domain.
Section 1. Mobility and City Scale. Let's kick things off with sports and entertainment. Picture a packed stadium. The network protocol here is usually Bluetooth or personal area networks. Interestingly, latency demand is actually pretty low for the fans in the seats, but we rely heavily on the cloud to crunch massive amounts of historical, biomechanical data from the athletes. And that introduces our very first core constraint, dynamic mobility. Just think about the physical reality of a fast-paced soccer or football game. How on earth do we maintain continuous, unbroken data streams from hundreds of fast-moving wearables? They're on the players, inside the ball, on the referees. If an athlete sprints from one end of the field to the other, they are rapidly crossing multiple network router boundaries. In an older, legacy system, that connection just drops and has to reconnect, and that completely ruins your real-time analytics.
Well, the solution is the IPv6 imperative. The old IPv4 system, with its tiny, exhausted 32-bit address space, it just completely cracks under the pressure of thousands of wearables. IPv6, on the other hand, gives us a massive 128-bit address space. I mean, that is enough for literally every blade of grass on that field to have its own IP address. But more importantly, it allows for dynamic addressing. As the device physically moves from Zone A to Zone B, routing tables are recalculating in real time to prevent connection drops across those boundaries. It is elegantly mapping network logic directly to physical movement. Now, scale that up to smart city transportation, and the whole game changes, because the geographic scale is so incredibly massive, we have to rely on LPWAN protocols like LoRaWAN. The processing becomes a hybrid of edge and cloud. And because we're dealing with civic infrastructure, security is absolutely critical. But the defining hurdle here is what we call diverging latency demands. You are suddenly managing vastly different data priorities all over one single, unified urban network. Imagine trying to manage all these diverging priorities at the exact same time. On one end of the spectrum, you've got completely delay-tolerant tasks. Think of smart parking sensors sending tiny, infrequent little payloads. It's perfectly fine if that data takes a few seconds to register. But on the complete opposite end, emergency response systems. Automated disaster routing requires immediate, uncompromising, mission-critical network priority. The city's architecture has to intelligently juggle both of these extremes simultaneously.
Section 2. Smart homes in retail. Moving indoors to the smart home, the network becomes highly localized and low power. We're relying on protocols like Zigbee and Z-Wave here. Processing happens deeply on the edge, mostly because, well, you want your living room lights to turn on instantly, even if your internet provider is having a terrible day, right? But the home is a notorious battleground for our next constraint, protocol fragmentation. You've got all these overlapping, totally incompatible standards trying to share the exact same physical space. The fix for this absolute chaos? The Edge Gateway. Think of it as a universal translator. Imagine a totally fragmented mess. You've got a Zigbee light bulb, a Z-Wave security lock, a Bluetooth speaker, and absolutely none of them speak the same language. The Edge Gateway sits right in the middle, translates those incompatible proprietary protocols, and securely routes them into one unified, manageable HTTP or co-op stream. It brilliantly brings order to the chaos.
Okay, let's step out of the living room entirely and into the global supply chain, where billions of physical items are moving every single day. This is a delay-tolerant, incredibly cloud-heavy environment built specifically for global inventory tracking. And the constraint here is massive. It's all about throughput and decoupling. How do you seamlessly track a shipment from a factory floor in Shenzhen all the way to a retail shelf in Chicago to enable these new product-as-a-service business models? To pull this massive undertaking off, the industry leans on a really strict three-step framework. Number one is physical tagging, utilizing RFID to overcome upfront cost barriers through cost-benefit sharing. Number two is the EPC framework, or Electronic Product Code. This global network uniquely identifies items, breaking down exactly what an item is using headers, filters, and reference numbers. And number three is billing integration. That's the magic step that transforms the physical movement of a tagged box into a fully automated financial transaction.
Here's the catch, though. Reading millions of tags creates catastrophic network overhead if you're using traditional, tightly coupled APIs. Having every single scanner directly talking to every single database, it just becomes a tangled, fragile mess. The elegant workaround is the MQTT broker model. Publishers, like your RFID scanners, send their data to a central broker. That broker sorts it by topic, something like warehouse/aisle 4, and then your databases simply subscribe to listen for that specific topic. This strict decoupling of sender and receiver prevents total network chaos in these crazy high-throughput environments.
Section 3. Mission-critical healthcare. In healthcare, the stakes shift to maximum intensity. The protocols move to highly specialized, secure Wi-Fi. I mean, we're talking ultra-low latency demands here, literally life or death. And processing relies strictly on edge and fog computing. Why? Because the core constraint here is the sheer vulnerability of the cloud. Transmitting continuous, raw biological data over public networks is just an unacceptable privacy and physical tampering risk. No hospital is going to risk that. So, how do hospitals actually secure your vitals in real time? They rely heavily on fog computing and edge AI. Down at layer 1, patient sensors are generating continuous, raw biological data. But instead of blasting that directly up to the internet, it goes to layer 2, fog and edge nodes that are physically locked inside the hospital building. Federated learning models analyze anomalies locally in real time. Only anonymized, non-sensitive summary metadata is ever sent outward and upward to layer 3, the cloud, for long-term historical storage.
And if you're sitting there wondering, well, why can't we just use faster cloud connections? Just look at the math. It mathematically makes the case for the edge. In a strictly cloud-centric architecture dealing with high-frequency hospital data, you get bottlenecked by distance and bandwidth. You end up with roughly a 4.8% packet loss. For life support systems, that is mathematically dangerous. Now contrast that with an edge-centric architecture using optimized, localized bandwidth. That packet loss drops to an incredibly reliable 1.6%. Throughput practically doubles, and communication overhead is drastically reduced. It definitively proves exactly why healthcare demands localized processing.
Section 4. Synthesizing the future.
When we pull back and look at the whole picture, this giant puzzle finally becomes clear. Every single domain we've talked about, sports, city, home, retail, healthcare, they all must explicitly tune their protocols, latency demands, and architecture to match their own unique physical reality. Sports needs dynamic mobility with IPv6. Cities need to handle divergent latency. Homes need gateway translators to fix fragmentation. Retail relies on MQTT decoupling, and healthcare demands edge AI for federated data privacy. So, what's actually on the horizon? Because right now, let's face it, we exist in a state of highly fragmented IoT. Devices are locked behind proprietary gateways. The big evolutionary leap we are moving toward is the semantic web of things, or WOT. This relies on standard RESTful principles. We're talking about applying standard web architecture directly to the physical world. It uses linked resources, modeling physical functionality with uniform interfaces, and it uses webhooks, syndicating data only when a physical event actually triggers a callback. That completely replaces highly inefficient network polling.
Which brings us to the ultimate grand vision, the architecture of the physical world.
The future isn't just about making individual devices smarter, it's about seamless interoperability and ironclad security right at the edge. It is about integrating these totally diverse domains so that your smart home can securely interface with the smart city, which in turn interfaces with smart healthcare, all while completely respecting their distinct underlying physical laws.
I'm going to leave you with this defining thought from our source material today. IoT is not about devices, it is about mapping digital architecture to physical constraints. I love that. The next time you look at a smart thermostat or a fitness tracker, don't just see a gadget. Try to see the invisible, complex architecture bridging the digital and physical worlds. But it does beg a pretty massive question. As these 5 massive domains finally begin to merge, what happens to our physical privacy when absolutely everything, everywhere, is talking at once? Thanks for joining me on this explainer. Keep exploring, and I'll see you next time.